So this is good, right? So let me just mention a few things that some of the questions that came up. Who was talking to me regarding the issue queue? Right now, I was talking to somebody. Right? What's your name? Sorry, Ishant. Ishant was talking about how do we. So the question is, okay. In this particular case, what I'm saying is you can schedule instructions whose operands are ready. The naive way of checking if the operands are ready is check if T1 has the result that you need, T2 has the result that you need, right? That could potentially be very inefficient. The way it actually works in most of the process is essentially you say, well, as soon as this instruction finishes, which essentially is just, it finishes and it writes its results into T1, it sends out a broadcast message saying, well, T1 is now ready. Anybody who depends on T1 can sort of, start processing. You can mark that instruction as being ready to schedule as soon as its operands are ready. So in this particular case, when T1 is written to, there would be a broadcast message going out. R3 is already ready. T1 is now ready because the earlier instruction has finished, which essentially you can think about that as this instruction having another field which saying whether it's ready to be scheduled or not, right? So as many instructions that are, have sort of this tick mark against them which says it's ready to be scheduled can potentially be scheduled in parallel, right? That's one thing. The second thing that I forgot to mention, that the success of this endeavor depends on the fact that you have sort of multiple ALUs already present. So if the case was that I have all these instructions that are ready to be sort of scheduled at any given point in time, but I don't have enough ALUs to execute them on, then it doesn't really make sense, right? So if let's say, which essentially gives rise to another very interesting question. How do I decide how many ALUs should I have over there? How would you decide? Given what we have talked about so far, if I was to design a processor and say, well, okay, these are the number of ALUs that I should have, how do you decide that? How would you go about deciding it? Dependent size of the instruction queue. Okay. What else? That's close, but not exactly. What is the metric that I would need to consider for making sure that I should have 4 or 8 or 16 ALUs? So in this pipeline, right? In this pipeline, I need to figure out, I need to have, let's say, 10 ALUs. What are the things that I should look at to say that I should have 10 ALUs? Find the? So let's assume that power is free, which is a terrible assumption to have, but let's assume that it doesn't cost me anything to have a certain number of ALUs. Let's say I'm limited by storage size. So I just want to figure out, it's an interesting question, I want to figure out whether I should have 8 or 80 ALUs. What should I be looking at? Okay. I could potentially issue, right? So essentially I would, that's a good point. How do I find that out? So what Newton is saying is that I should look at the maximum number of instructions that I could potentially issue is the maximum number of ALU should have. Okay, fair point. How do I figure out how many instructions I can issue? So think holistically, think from the program down, right? Okay, think even at a higher level of abstraction, right? Think about what are these? I mean, what is this? This is a program, basically, right? So go to a higher level of abstraction and think about what it is that you need to be looking for to decide how many ALUs should you have. Okay. All right. That's almost there. Topological sort of what? Okay, of? Right. So that's a good point. What's your name? Frank. Okay. All right. So Frank makes a good point, right? So what we need essentially to do is figure out at any given point in time, how many instructions could I potentially schedule? And for that, I need some empirical data, right? Where is that empirical data going to come from? Whether it should be 8 or 80, where is that data going to come from? Anything that is done in computer architecture is done on what? So all of these are essentially programs, right? So I have a wide array of programs that I'm going to run on a particular processor. This is a desktop class CPU. It's going to run desktop class applications, right? So what I need to do is essentially look at the programs that I have, figure out the kind of dependencies that are there, and then do some sort of analysis and figure out, okay, at any given point in time across this class of programs that are going to run on this CPU, I will never have 8 or 10 or 15 instructions that potentially can be executed in parallel. Out of those 15, 2 are going to be integer adds, 3 are going to be multiplies, 4 are going to be divides, things like that. And then I decide, okay, these are the number of ALUs that I potentially should have in this sort of class of process. Make sense? Right, so from the bottom, from the top down, yes. Okay, so a processor runs programs, right? You have different classes of process to run different classes of programs. All right, okay. So let's say I want to design a processor. Well, the question was, how do I figure out how many ALUs I should have? The question that you need to ask me is, what am I designing this processor for? What are the class of programs that are going to execute on this processor, right? So let's say there is a class of programs which essentially has 10, 15, 20 different programs that are going to run on this processor. I take those programs, I do the sort of dependence analysis on the assembly language, representation of those programs, and figure out, well, okay, at any given point in time across this big a window, let's say a window of 500 instructions, I never have more than 15 instructions that can potentially be executed in parallel, right? Out of those 15, this is the breakdown of the kind of instructions that I will have, and based on that information, I can figure out, well, okay, these are the kind of ALUs that I want in my program, or in my processor, sorry, right? Make sense? All right, so let's talk a little bit more about out-of-order implementation, right? So this is a very high-level abstraction of an out-of-order processor, right? So I have introduced a few units. This unit, which is called the HUQ over here, excuse me, allows me to schedule instructions in parallel, right? This unit, the reorder buffer over there, is essentially a way of making sure that the instructions commit in program order, right? So here you are executing them in parallel, but the instructions are actually being committed in program order because they are present in the ROB, or they are made to go into the ROB in program order, and an instruction is only going to commit its state when it reaches the top of the ROB, right? So as soon as this instruction completes, reaches the top of the ROB, it says, well, okay, nothing bad can now potentially happen because everything else that was before me has now finished and committed its state, right? So if this instruction has reached the top of the ROB, everything else before it has actually finished, completed, nothing can go wrong. Well, okay, I can commit my state, which essentially means I can take the result of T1 and copy that into R1, right? And you can do that for the rest of the instructions as well. Is that a good idea or a bad idea for committing? So what I'm doing is I'm placing my result in a temporary register T1, and when I commit this instruction, I copy the results from T1 into R1. Is that a good idea or a bad idea? Okay, how many of you think it's a bad idea? How many of you think it's a good idea? Okay, so I say it's a bad idea. Now you have to tell me why is it a bad idea. So again, the idea here is that we have gotten the point where we need to commit the stage of, or we need to commit instruction I1, which is essentially taking its result from temporary register T1 and putting that into the register R1, which is the actual intended destination for the instruction 1 over there, right? Why is that a bad idea? Why? Okay, so we're talking about just one instruction over here, right? This instruction, I1, right? And we are talking about a specific commit stage where I'm saying the instruction has finished, now it's ready to commit. Its result is in temporary register T1, and in order to commit this instruction, I need to copy the state or copy the register value from T1 into R1. And I'm also contesting that it's a terrible idea. Why is this a terrible idea? And the answer lies in the sentence that I just said previously. Is copying registers a good idea? Ever? If you can avoid copying data, I mean, if you go look up literature in architecture, everybody says most of your problems, your energy consumption, your latencies arise because you have to copy data here, there, everywhere, right? Copying data is always a terrible idea, right? So essentially, if I have this naive sort of an implementation of an out-of-order processor where I'm saying that I put the register results in this temporary register T1, and then when I'm ready to commit, I copy the contents of T1 into R1, bad idea, right? Don't want to copy data, ever. So now you need to find a sort of a better implementation of executing this abstract notion of an out-of-order processor, but by not committing the heinous crime of copying registers from T1 into R1 and T2 into R2 and so on and so forth every time you want to commit an instruction, right? How do you sort of go about doing that? Right, so let's not go here. Let me, okay. So this is where we are, right? Now, how do we sort of go about doing that? So the terrible idea was copying T1 into R1. Can we do better than that, right? So the answer is yes, of course, because otherwise I would not be talking about this as if, you know, it's a. Right, so in this case, again, as I mentioned, it's a very abstract sort of an implementation, right? In this case, you have the R1 and R32, which is essentially the set of registers that are exported by the hardware. And then you have this extra registers, T1 to Tx, essentially, right? Which are essentially the temporary registers that you use just for rename. Right, so that's why we had these rename registers, and when we had this set of logical and architected registers, right? And again, the idea was that once you're done here, you copy the contents over here, which is not good, right? So what we are essentially going to do is we are going to merge all of these two boxes into just one box and call it the physical register file, right? So essentially, let me see if I have the diagram over here. Is this, right? In the previous diagram, what we had was essentially we have two sets of register files. One was a temporary register file, the other one was the architecture or the logical register file, and then we are copying things back and forth. Not going to do that anymore. What we're going to have is essentially this large sort of register file, which is only going to have registers which are we're going to call P star registers, right? So we had T star and R star registers in our previous example. Now we are only going to have P1 to P64 in this case. And what we are also going to maintain is essentially a level of indirection, right? So somebody very famous in computer science said everybody or every problem in computer science can be solved with one extra level of indirection. Anybody knows who that was? So again, almost every problem in computer science can be solved by adding one extra level of indirection. Anybody knows who that was? Huh? Probably not. If I'm not mistaken, again, I could be. I think it was Jim Gray from Microsoft Research. But again, I could be wrong, and you need to look that up. But anyways, that's exactly what we're going to do here, right? We are going to add an extra level of indirection, which essentially tells you where the current value of any particular register is, right? So what we're doing over here is initially we were using R registers, which was the architected registers that are exported by the hardware. which are essentially the registers that the compiler uses to produce the assembly code, right, which is essentially what we get over here. Right. Now what we are going to do is essentially say that our hardware has a set of registers, a register file. This is actually larger than the set of the architected register file that is exported by the hardware, and we are going to use this combined register file for maintaining the information that we had before, right? So we had temporary and architected. Now we just have permanent registers. So the the renaming that is going to be done is going to be done by separating this physical register file in two sets. One is essentially the initial mapping, and the rest of the registers are essentially going to be used as the free register pool. So let me just quickly see if I can kind of get over that. Okay. So what we are doing over here is essentially, in this case, let's say I have 64 registers, right? The architecture still exports 32 registers. So R1 to R32 are the registers that are exported by the architecture, which essentially means the compiler or the assembler or the compiler can produce instructions using R1 to R32. Now, in order to rename that, what we are doing in the previous case is we were using T registers to rename, right? In this case, what we do is we set the initial mapping to be R1 maps to P1, R2 maps to P2, all the way to R32, which essentially maps to P32. Now, since my register file, the physical register file has 64 registers, which essentially means that P33 to P64 are kind of lying vacant right now, right? So I can use those registers, P32 to P64, as my rename registers. They are going to serve the same purpose as the registers, the T star registers that we used in the previous example, right? So what we're going to do over here is when I rename the previous set of instructions that we saw before, what we did here was R1 and R2, and the contents were written into T1 over here. In this case, my set of free pool registers or the rename register starts from P33 and goes to P64. So what I'm going to do is I'm going to rename them P1 to P2 because R1 and R2 originally mapped to P1 and P2, and because I need to find a free register to write the contents of this particular operation in, the first free register is P33, and that's where I write my contents, right? So essentially what I have gone from is two sets of register files into one single unified register file, and now I'm maintaining a level of indirection which tells me where the most recent value of any register, any R register is now located in, right? So at this point in time, when this instruction finishes, right, in the previous case what we were doing, we were taking T1 and copying that into R1. Now when this instruction finishes and it has the result of what is supposed to be in R1 in P33, what is the way in which I can convey this information that the latest value of register, which is supposed to be in R1, is now in P33 to all the instructions that are following this particular instruction, right? So again, let me state that one more time. Initially, what we are doing was this register was being renamed to T1. Now, what I'm doing is I'm using one of the physical register files, which is part of the larger register file. I'm saying that the result of R1 is now in P33, right? Now I need to tell all the instructions that are following this instruction that if you need R1, it's now in P33. What can you do for that to happen? And again, going back to the quote of Jim Gray, how do you connect those two dots together? What I'm saying is everything can be solved by using one extra level of indirection. And what I need to tell everybody following this instruction is the fact that R1 is now in P33. How do I reconcile these two different things? Huh? Anybody? Absolutely, right? So all I need to do is maintain a table, which is a level of indirection, right? So I say initially it was easier here because this is what I said, right? I mean, I said any instruction that sits here is going to use T1 automatically. Now I can't say that because I want to make things a little simpler. So, but I still want to say, well, if this instruction, excuse me, if this instruction is over here, then its destination register is somewhere. How do I do that? I maintain a map, right? So the way I maintain a map is by doing something like this. So I have added two more structures in this case, right? So what you'll see is this figure is a little different from what we saw before. Excuse me. What has now gone away is essentially the temporary register file, right? So the temporary register file and the architected register file, those two units have been combined into this one big register file which has 64 registers now. What has now been added are essentially these two sort of maps over here. One is called the speculative register map and the other one is called the committed register map, and we can talk about these in a little more detail. But in essence, what they are essentially maintaining is levels of indirection, right? What this is essentially saying that at any given, at this point in time of program execution, what you're looking for, if you want to look for the latest value which was being pointed in register R1, it's now sitting in P36, right? The latest value of R2 is sitting in P34. All the instructions that are following this sequence of instructions, if they need the latest value of any particular register, they can look at this register map, figure out which register that it is that they have to read, and then sort of just go and read that register, right? Now, how does this make things simple from the earlier situation that we had? Does this make things simpler? There is no need to copy the values, right? So, so one thing that we have completely avoided, excuse me, is the fact that there is no need to copy the registers between the temporary and the permanent register file. Now, that comes at the expense of what? Sorry? Okay, so yes and no, right? So if I was to make the assumption that my temporary registers plus my architected register added up to 64 in my previous example, which was essentially a representation, right? And if my physical register file has 64, that doesn't change things. And let's go with that assumption, that T and that R initially added up to 64, now I have 64. That doesn't change anything. Assuming that. What else does that come at the expense of? So no register copying is happening, which is absolutely great. The extra thing that is happening is essentially this lookup over here, right? Every time you need to sort of read the contents of a register, you have to go and look up this particular register table at certain point in time, right? But empirically it has turned out that this is a worthwhile expense to pay. Copying registers is terribly expensive both in terms of latency as well as power, but having an extra level of indirection where you just have to look up where it is that you have to go to read that particular register value, and is much more easier, right? Okay, and then there is this committed register map, which I don't think we have the time to talk about, but again, this is essentially, think about it in terms of the actual architected state of the processor, right? So this sort of level of indirection is for all the instructions that are currently being executing, right? So that's why it's called the speculative register map, because it might have instructions that are being executed speculatively as well. But this register map essentially tells you where the architected state currently is. So remember what was happening in the commit process that we had over here. In this particular case, what was happening in the commit process? The instruction reaches the top of the ROB and then decides, well, okay, now I have to copy the contents of the register, right? That was what was happening. In this case, what would happen on a commit is essentially something very simple. All you need to do is potentially just change this mapping, right? So if that instruction has now committed, and then you say, well, this instruction is now at the top of the ROB, and now I want to commit this instruction, all you say is, R1 is now in whatever, P45 now, and you're done, right? There's no copying, all it does is just updating a value. Yes?
Copying is also updating a value and storing a 16-bit value in the register.
Right. Absolutely, but these are not 16-bit values, right? This is not a complete register. The size of this depends on how many registers you actually have. So this is essentially a 6-bit value, right? So this is much more easier and less costly. All right, so I think we are out of time. I'm here for the rest of the day as well, so we can talk a little bit more about these questions. Okay, all right.